系列数就不了了。技术在。
Okay, let's get started. And welcome back. This is actually this is the last day for the assignment one. Remember to submit. I know some of you are still strapping on that, but don't, as I mentioned in the announcement, don't worry about it. So the point is to explore and to experience it. So no matter what you get at the end, even your model may fail in between. So write down what you have learned from there. That's the most important part. Don't worry about the performance that much. So I actually received some feedback like you might feel this is a challenging task, but it turns out at the end they figure out it's not that hard because we actually provided all the necessary code already. You just have to combine this code together as a run of the system. So anyway, in either case, we will discuss that assignment later. But I guess you really experienced something there in Beijing. Like I received a question like, what is the right number of layers, right? So what is the right size for the convolution? So I received a lot of questions like that. So today we're going to talk about that a little bit to figure out something like if there's a way for you to check how exactly the network is working. But because basically deep learning models are black boxes, it's not easy to figure those stuff out. I mean, even we check the loss function there, but there are other methods between there. So anyway, today we're going to introduce the CAM, attention, and transformers. This is basically 3 keywords for today. And here's the outline. And so, because you are working on the programming, and you probably already have the code. We provided a lot of code during the tutorials, and we uploaded them to the Blackboard as Koi explaining videos. But might happen like some of the students, they may miss the lecture or tutorial still. They still got questions about the connection between the concepts and actually code. So maybe we should take this opportunity to link them a little bit. So so far you really worked on the data set. You even collected by yourself, right? So there are some concepts or code should be introduced. And so you have data sets, and during training, there are different techniques to help you to avoid some of the situation of the training, or to simplify your process of training. So one of them, the key concept is a batch. So I guess if you're using the deep learning or you are studying the sample code we provided for neural networks, you should already see this term, right? The batch. The batch is basically a subset of the data sets, like shown here. So it's a subset, and when we're doing training, we're not exactly feeding the samples one by one to the model. We're actually feeding it in a manner of batch by batch. This has been proven to be more efficient or even more effective. A batch is a subset, meaning like there are several samples there. We call them a batch size, like what's shown in the sample code we provided. We're using the 32, right? So actually, the size affect the performance a lot. The reason is when we're using batch for training, we're training it in batch manner. We are not updating the gradients by samples. We're updating the gradients by batch. So for every batch, we update that once. This turns out more efficient than updated sample by sample. And at the same time, because you're updating it that batch, so the updating process is actually something we conclude from that batch of samples, rather than if you're updating them sample by sample, it's more random, right? Because you can't make sure that for every sample you get a perfect information for updating the gradients. But if you're pulling samples together, in case there are some noises or errors there, they will be averaged out by updating together. So that's the idea. It's more efficient, and also it can avoid some problems. Otherwise, if you update them sample by sample, it quite makes the updating process more random. And in terms of the gradient distance, maybe it will go here, there, here, and there. So it's not that stable. And anyway, batch is something people figured out will be a better choice. So that's a batch. And shuffle. Shuffle is the idea like you're playing the cards. You shuffle the cards to put it into different order to randomize it. So you could shuffle the data before you divide them into batch. So it will, when data collected, sometimes the consecutive samples usually fall into the same type. Like when you're collecting this gesture, and usually you collecting one by one. In a consecutive time period, you basically collect the same gestures, right? So shuffle can help you to randomize those samples and to avoid a situation like the samples in the same batch are too similar to each other. So in that case, that batch might be biased to some of them. In case of the gestures, it's biased to a certain gesture here. So it will not so good because we're actually looking for a process which the noises and errors can be errored out during the batch updating process. If they're biased, your updating will bias to somewhere. It wouldn't average something out. So it will sometimes better shuffle it. Okay, here's one, and this is actually the code help you to prepare the data set into batches. So here you can see, you just have to tell what the data set is. You gave the batch size and whether you want to shuffle it, and number of workers doesn't matter that much. It's just telling you can you can put the preparing process into parallel manner. So this is a code. And also data loader is some kind of tools to help you to split the data into batches, and also there are other functions could help you to manage the data, and so you don't have to write it by yourself. So it's a tool anyway. So rather than do it by yourself, and also when you're feeding those batches or you are browsing those batches, here is an iteration you can use, which every time in this loop, it will give you the batch ID and also the samples related, the labels for corresponding samples for you, so you can use them directly rather than you have to check the IDs of samples. It's already done it for you. So every time after it has been divided into batches, and every time this will give you one batch. So you can use this for loop to get batches and also conduct your training process. This is the code, and also about the networks. And here I'm showing the network in the quick start we provided in the tutorial today. You see here is the simplest convolutional network where we have one convolutional layer and two fully connected layer there. So but the most important part is when you're designing a network, you have to make the shape of every layer right? So that's quite important. You can see here, we should have some input. If you have used the quick start, you know that every image there is with a size of 20 by 20, 28 by 28, right? The digits, handwriting digits, and that's a gray image. So in that case, for every image, we have only one channel here because it's gray image. It's not RGB, 3 channels. So that's the input size. And when we're applying the convolution, it's actually when you're doing it on images, it's 2-dimensional convolution. So we're using COM2D there. So you could see here, because our input is one channel, so we have to put it's the number of channel 1. However, after that, as I mentioned, you can actually extend a number of channels rather than stick to the original number of channels. So in that case, we want it to be spanning 32, meaning like you could analyze do the filtering on original images from different perspectives. So here we have, we are expecting 32 perspective of that convolution. So you can do the convolution in different ways there. There are 32 ways of doing it. So this is what we are expecting. So that's the up channel is 32. So after this convolution, it's what becomes of 32 channels, and the kernel size is the filter size, right? We put 3, so meaning that like the filter is a 3 by 3 filter kernel there. So then after that convolution, you are supposed to have something of this shape. So here you could find something like at the spatial dimension. This is a spatial dimension, right? We extend the channel dimension to 32, but at the spatial dimension, the size has been shrink. Why? Do you remember? Yeah, that's right. So, because for the corners, or edges, you don't boundaries, original image, you can't do the convolution. So you skip that part, making it shrink at the boundary of that image. So that's will deduct 2 pixels from here, making it 26. So just have to remember that. So it becomes this shape. So when you're doing the fully connected, you're adding the fully connected layers, and you have to collect all of them. I mean, every neuron there to the next, for every neuron of the next layer, right? So in the next layer, we have 128. So that's the output of the first fully connected layer. But the input size equals to those numbers altogether multiplied, right? So meaning like you're collecting every neurons here to every neurons here that way. So and after that, it's between the fully connected layers, neurons between all of them. So it's 128 to 10. The reason we have a 10 as a final layer, because we're working on the handwriting digits, right? There are 10 of them from 0 to 9. So that's the reason we have a 10 there. So this is basically, you could see from here, the actually shape to the actual code one by one. Right? That's the reason we have this. I guess some students really work on it, and I have to explain further. And so another concept is, once your network has been prepared, you have to conduct the actual forwarding process, meaning that like we call it feed forward, meaning we feed some of the samples to the network and network will process it. So you could see from previous slides, we're actually defining, So we're actually defining the structure of network. We haven't defined how this structure will be used. So the forward function is defining such kind of thing, telling how the order of the feed forward process. So here you can see the X is input. So from here it's an image. So image will be sent to the convolutional layer, which we have defined, processed, then the output, we're using the same variable there. So this X after the convolution is different from that X, right? So the X right now after the convolution will be this one. This is the X. Then, but as mentioned, it will be better to add some activation function after that process. In that case, we're using the ReLU, which we have introduced previously. So ReLU will be added to here after you got that X, ReLU will be down. Then that X will be replaced with the result by the ReLU function. So the X is changing constantly. Then we use a flatten process. Flatten is something like put all the neurons as one line. So that's a flatten process. The process doesn't change the number of neurons, but it's changed the shape of that neuron. So this is a flatten process after the ReLU. So meaning that up to here, you actually got a line of neurons there. And it will be connected to, because right now we're going to use the fully connected layers. So this line of neurons, each of them will connected for all the neurons of the next layer. So that's the reason you feed them X to the fully connected layer, and you got another X. And in the same way, we have the ReLU as well. Then after that, you have the result has been fed into the last layer, there, fully connected layer. And at the end, you have a softmax as activation function. Why do you need a softmax? Oh, yeah. Yeah, that's right. Because we have to normalize the output into a certain range. And softmax actually put output in the range of 0 to 1. And it's analog to the probability. It's some kind of likelihood. Because right now we have 10 outputs. If we normalize the range into 0 and 1, meaning like this 10 neurons can correspond into the 10 handwriting digits. because we have 10 of them, meaning like we have 10 labels there. So as long as we build up this correspondence between those outputs and that labels, we could consider it as likelihood of probability. So then we can evaluate with loss function to see how well it matches our expectations right now. It's a ground truth of handwriting images, handwriting digits there. Okay, so after that, you just output the result on the 10 neurons there. But right now, it's just the feed forward process, and you got probability as a vector with a length of 10. And each of them are telling you a probability, a likelihood, like how likely the input contains handwriting digit 0, how likely it's a 1, how likely it's a 2, so on and so forth, or something like that. Okay. This is feed forward. And after feed forward, we have to do the back propagation, right? So the start and the back propagation is started from the process of calculating a loss. So we have to define a loss function. And most of the time we're using the cross entropy loss. It was defined here. It's basically a probability of the ground truth, meaning like what you're expecting. Let's see, right now we have maybe use a pen. So let's see, right now we have something. This is what we are expecting. Let's see, it's let's see, it's a 1. Okay. The input with a 1. So we can use a 1 hot vector to represent the ground truth. Right now it's 1, 0, 1, and the rest are just all 0, because this representing the 1, right? The first position representing 0, this representing 1, 2, 3, so on and so forth. Let's call it the ground truth, because this is what we are expected. And also we have something predicted. It's actually output here with the same shape like what we are expecting. But it's most of the time here we'll have something like 0.1, 0.8, 0.05, and so on and so forth. This 0, 1 telling us it's with something like 10, a probability of 10% to be 0. And second one is something like it's with probability of 80% to be digit 1, and so on and so forth. So here we're actually comparing these two stuff. Here is outputs. Here is what we're expecting. We got two probabilities there. So if you're familiar with the entropy, and this is actually the entropy, right? Something like the entropy. So that's the reason it's called cross entropy loss. So I don't want to go to further detail. This loss will become larger when those probabilities are the same. And it becomes smaller when these probabilities are the same, and it becomes larger when they're not the same. I mean, that two vector. So the difference of that two vector is larger, which will make this loss function larger, output larger value. If that two vectors are very similar to each other, and this loss function outputs a smaller value there in between. So you can check it out by yourself. This is loss function, and also atom is another way actually defining how you update those gradients, because after you have the loss and you calculate the gradients, but we have, let me introduce the learning rates. This is what we have introduced previously, right? We don't want to put all the gradients updated back to the parameter, because that might be more risky or more too much aggressive in between. So we're taking a certain part, like 0.05 of the gradients, updated to the parameter, something like that, defining by the learning rate. This is something we have introduced. However, what is atom? Atom is one, is kind of strategy for updating that, because the atom optimizer actually defines something very similar to what we learn in the physics, the moment, meaning like if one object ran with a higher speed and you have higher moment there, when it's going slow and the moment is smaller at the same time. That's what we have in the physics, right? So when you're updating the gradients, there is something similar. Sometimes you're updating it's much quicker. Sometimes might be the gradient change is smaller. I mean, it's like it's snow, right? So by taking that moment idea to here, you can define some kind of moment on the updating process. So when you're at that moment, the updating, you could consider there is a ball because it's gradient descending. It's like a ball falling down to the valley, right? So you could see the speed there as well when you're updating it. So at a certain moment, you have a speed there. So simply saying the atom algorithm will check out that speed and define how greedy you can to update the gradient. Sometimes it might be greedy. So it is taking very greedy updating, like when it's here. But sometimes you have to be careful, like when you're going to here, right? You got to slow down to update a little bit, or something like that. So this is atom strategy, and in addition to atom, we actually have a different strategies there, and people are keep proposing new strategies there, which might fit into different scenarios of application. So that's what it is. Those 4 lines of code actually define defining something for the most important is the last 2 lines of statement, defining something for back propagation. But it's just defined. We haven't used it. So the place we're using it. So it's here. Here are putting together all the necessary steps for training. So there are more ideas here. Let's check out this part first. This is asking where the learning has been done. So this is actually the learning process. You could see here, like we're using the iteration we have introduced. Every time, as mentioned, for each iteration, you get 1 batch. And that's a set of samples. You got that samples and load them into devices, labels into the devices as well. Then right now, you can call the model by feed into the samples. This is a feed forward process. Then after that, you can use the loss function you defined in the previous slides, right? So you calculate the loss by comparing between the ground truth the ground truth right now is the labels, right? So this one is actually the outputs. If you check out the forward function, and this is actually the outputs vector. So by comparing two of them, you got a loss. Then you initialize the optimizer by clean the gradients. Then you do the backpropagation and update the gradients. And you move to the next step, meaning that you actually update them into parameters. This is calculation of the gradients. Then you use the gradients to update the parameters here. Okay. Then you can repeat that process for all the batches. Then the training is done once, meaning that all batches have been used. However, people figured out sometimes, most of the time, it will help if you can train it multiple times on the same data sets. So that's another term called epoch. So it's here. You could run the training on the same data sets for 3 times, meaning that you get every such kind of iteration, you can call it an epoch. So that's basically, we'll run this process for a certain number of times. That's another term, and also its connection between the concept and the code. Okay. Okay, that's it. So I guess most students has already tried them out, and so let's do it this quick. And last concept I want to introduce is the cross-validation. Actually, in the rock, paper, scissors game and sample code, we run the cross-validation. You probably already see this, right? Cross-validation. So what is cross-validation? Cross-validation is something like for the same data sets, you can divide the training and testing in different way. Like you can use this part for training and the rest of them for testing, a small part for testing. And sometimes you can actually change the order. You take those at the beginning as a testing subset, and the rest of them for training. Why we're doing that? The reason is because the training data sets usually are with some kind of bias to some kind of classes or labels there. By dividing them into different way, it's more or less can address that bias to see how your model can be generalized into different situations. So the N4 is, the N stands for the number of validations you will do. So here we divided into the data set into 3 different ways. That's what we call a 3-fold. You run it 3 times. And so by the cross-validation, it's like you verify your model in different way and see how see its performance. It's you got a good, it's doing good in the cross-validation, meaning this model also possibly can be generalized to different cases. Otherwise, it will be biased to a certain type of distribution here. So this is a way of checking that. Okay. Okay, that's it. That's a brief introduction by connecting the concepts to the actual code. However, because you're doing assignments, right? I guess most effort you're spending on assignment 1 is to prepare your training data sets, right? Because we already actually have all the code for training. and testing, but what we don't have is the training data sets by yourself. So I guess most students are taking efforts on that. However, you probably already experienced collecting data sets is a costly effort process, right? It takes a lot of time and efforts because you have to collect data and you have to label the data, right? And right now you're doing it in a really small scale. However, in real application, you have to deal with it in a really large scale. So it takes much more efforts, really. And it turns out like in a lot of application, we can take advantage of this publicly available data sets. Like this one we have introduced is ImageNet. You see here, we got something like 10 million data sets, more than 10 million data sets, and with more than 20,000 classes here. Those are with images. At the same time, the label of the image is prepared. So it's really large. You can conduct a large scale training based on those data sets. And actually, I might have introduced that this ImageNet is actually one of the main reasons making the deep learning popular, right? Because deep learning need a lot of data and labels, but before deep learning getting popular, most of the experiments have been done on controlled environment, small data sets in that case. But after this ImageNet, we got the data in large scale, and we got the possibility and chance to train the classifiers in large scale. And here's another useful source. It's called paperwithcode.com. You can check out the latest arts of each of the data sets. And this is for ImageNet. And the results shown here is not up to date. I haven't updated. It's back to 2 years ago. I guess there are better methods they're developed in between. So anyway, you can check it out by yourself. And for different data sets, you can check we call it SOTA, meaning it's a state of the art performance on each data sets. But the ImageNet is so huge. So people, it's not so friendly for most people because they might have limited resources for running the experiments. So there is a simplified one, also very popular, called the CIFA. The CIFA 100 contains 60,000 images and with 100 classes there. It's in a much smaller scale compared back to the ImageNet. And if you're doing something, and this is a good point to start, because it can run it can be trained locally on your machine. And also there is an even smaller one, including 6,000 images and 10 classes there. So if you want to try some try out some ideas here, I guess these two data sets will be good to start. Not that small and not that big. CIFA is the data set. And here is the SOTA performance on CIFA 100. And also it's now updated. You can check it out by yourself to get a more up-to-date performance. And the COCO is another one for image detection and image segmentation. Image detection is trying to figure, because if you're doing a classification alone, it just give you some labels. Like for certain of the digits, it give you a 0, a 1 as an output label, but it wouldn't tell you where that character is located in that image. So detection is something beyond the classification. So it tells the label and the location of that object at the same time. So it's an image detection, and this COCO data set is for image detection. And at the same time, you can go further beyond that by tell the exact area of that object, and that's called segmentation. So we will introduce image detection and segmentation next week. So just let you know here, there are some data sets specifically designed for that purpose, and this is another one, and probably more commonly used for image segmentation, which will tell you the exact area of different concepts related there. So, okay. So, and okay. I can't introduce all of them. Those are just for example, and there are a lot of them there actually. But now we have both the models and data sets, and we back to the question which has been asked during assignment 1. How can we know the model are working properly? We introduced something to check the overfitting, underfitting last week, right? That's one thing telling you if the training are going well in a general sense, but it wouldn't tell you something like if the model are designed properly, right? Like the number of layers, like the size of kernels, if those are going well. So that's kind of different. The checking of the loss, development of the loss is a process to check the training, right? The training process. But we actually need something to tell us if the model are well designed, right? That's what we want. It's different dimensions, right? So required different dimensions. And also we probably could use the accuracy, precision, and recall to evaluate the performance. We don't exactly know how the network works. So that's the reason I mentioned at the very beginning, deep learning models are considered as black box. Yeah, so we don't know what happened inside. But fortunately, there are some probes we can use to check it out. So here is one which are very popular. It's called class activation mapping, also called CAMP in short. And let me draw something to help you to understand it. So let's see, we have an input as an image, and we feed it into the neural network. Let's see, it's a convolutional neural network. There are many layers there. And at the last layer, we apply the fully connected layer to do the reasoning. Let's see, those are fully connected. Or something like that. So we are actually connect each of the neurons at the last layer to every neurons in the next fully connected layer. Those are FC layers. Those are convolutional layers. And at the end, you have some kind of results, right? So the idea of the activation map is during the convolution, I probably have mentioned the spatial dimension, the information on the spatial dimension will be preserved, right? Because when we're doing the convolution, we're doing along the spatial dimension, right? But we change the channels, number of channels, meaning like we're sometimes summarize across channels, but we preserve the spatial dimension, right? The spatial dimension means these two dimensions, this and this. This gives us some kind of advantage, like for example, when there is an airplane in the original image, and every time, even after the filtering or convolution, the size has been changed, but the information about this airplane will more or less preserve there, right? Meaning that, let me change it to different color. Meaning like for this part of that image, its feature will summarize as the corresponding position of the feature map. Even we might have different channels there, but let me go back. So you might have different number of channels, but the correspondence at the spatial dimension will be preserved at the feature map. So meaning like you can take this certain part out, meaning let me take that out. Let me take it out with different color. So if I take this part out, it will be something like if we take that part out across channels, and this part of the feature will corresponding to this part of that image, and we can do the similar thing for other part, because as I mentioned, a information at the spatial dimension will more or less preserve, meaning like for this part, you can also take it out across channels. So this part is corresponding to this part. That's the idea. So there is some kind of correspondence in the spatial dimension, and we can take advantage of that in a way like we have a prediction at the end, and it's actually, let me change the color. Okay, so let's say here is a prediction. It's a probability corresponding to the airplane. So let's see. Here is a point line. It's pretty high. So meaning the network make a prediction as an airplane, right? When you have high responses here. However, before we're doing the reasoning, the feature map as the last layer, let's see, usually are supposed to be something like this. So in case it's making the right decision as an airplane, we need to know is it focused on the right part of that image. Meaning like it should be used the part containing the airplane to make a prediction as an airplane, right? Rather than at the other part. Sometimes it could be go wrong. Like if your data set is biased, let's say you have both airplane and ground vehicles as classes here, but when your data set is biased, sometimes you include a lot of sky related stuff there, and the model may focus on the wrong part on the sky rather than the airplane, right? So we have to make sure your model is actually focusing on the airplane rather than the sky, right? Otherwise, sometimes sky may work to help you to make prediction of the airplane, but it's not right. Um, um, in a sense, it's not focusing on the right part. So how can we check out that part? See if it is focused on the airplane. So it turns out you can check out how those neurons are activated when it's making the prediction of the airplane. I mean, by airplane here, I mean the part corresponding to the airplane in the original image, because as mentioned several times, the spatial dimension has been preserved. So the hypothesis is if that neuron are highly activated than others, and it will be used for the inference, right? So we can visualize how those neurons are activated. It's probably will give you something like those are less activated, and those probably are highly activated, and those parts are highly activated, activated. Anyway, it may roughly give you a shape of the airplane because those parts are highly activated, and meaning that network is focused on the right part. You can check activation for different classes to see if focus on the right part. So this is a general idea of doing it, but it turns out people figured it out by checking out the activation on neurons may not be that reliable. So turns out people figured out different ways of visualizing it. And this is the original idea of the CAM and class activation mapping is proposed. It's generally the same as what I have introduced. The only difference is this part. So at that time, people don't have too much understanding about this. So they think we might have to control the output so we can investigate it. So they insert one convolutional layer at the last layer of the convolutional, after the last convolutional layer, meaning this new inserted layer was taking the outputs of the original one, but in a way we want. Meaning, like for example, each of these channels corresponding to one of the classes we want, and they are connected into the final prediction there. So in that way, we know how each of those parts, how the correspondence will be, because we know the classes labeled at here, and we know that channels here at here, right? So for example, if you have the airplane here and the activation are supposed to be here. If you have the car here, the activation might be there or something like that. So by doing that, we can when we have output there, we can check it back on the corresponding channels, the activation of the corresponding channels, see if it is focused on the right part. And you're having something like that. Here you actually use these weights to multiply back to the corresponding channels because those are activation, those are probability, right? So by putting them together, it tells you how the prediction has been reached. So something like that. So You could check out here if it's making the right, if it's focused on the right part of that image by resize it to the exactly same size as the original image, and you stack them together to see the correspondence. So this is a way of checking it. This is the original cam is proposed. So here are more examples. You could see sometimes it work well, like those are for different stuff. They focus on almost like the right position, right? Especially for the hand, and most of the part has been covered, right? So it's not perfect, but good enough to tell us where the network is focusing on. Okay, later people grab more understanding there. The hypothesis, this is very popular camp called grid camp. The hypothesis is you don't have to rely on activation, and you don't have to insert additional layers to the original model, because actually when you're inserting stuff into a original model, it's changed the way of the reasoning sometimes. So in this paper, they propose to use the gradients. You can actually check out the gradients. When some part is used for reasoning, and the gradients of that part supposed to be larger than other part as well. So this is hypothesis, and they're actually using that to create a grid camp visualization. And this is for cat. You see here, there is a dog, there is a cat, but the focus is on the cat, meaning that network is focusing on the right part. And so I will skip detail. The difference between these two, generally speaking, one focuses on activation, the other focuses on the gradients. So that's the reason it's called gradient and grid camp. And further development on that is score camp. Score camp use very creative idea. Like if you want to check out if it's focused on the right part, you could do something like you got some other camp, like the grid camp there, because those can be used as a mask with the weight. Because if there's a higher response on that heat map, it's with larger volume, right? So if you put this mask on the original image, it will have the part focus. The network is focusing on stand out there, right? So when you're putting this mask on that original image, and if it's focused on the right part, it should, when you feed that network again to that neural network, because this is a way force the network to focus on the part you got from the CAM method, right? If it's right, it should improve the result, right? If it doesn't focus on the right part, what will happen? If it's not focused on the right part, let's say if it's focused on the background, the prediction wouldn't be good, right? So the idea of this is you can check out this unmasked result and this masked result to make a better prediction on how the network is work or focused on. You can summarize these two perspectives of it. So it's called a score camp. Here's another one. And also conceptor camp is actually a method we developed. So our hypothesis is, no matter the grid camp or the original camp or the score camp, they actually, when we're they are creating a heat map, they actually it doesn't consider the inter-channel relationship. They usually use a max pooling by summarize the information from each channel. Meaning like the spatial inner channel spatial information has been ignored. So we developed some kind of method to address that problem, and it's called concept CAM. And this actually can be integrated into different CAM methods. And you can see the result here. Actually, it's getting better result than the original one. Like this dog, and it's focused on better on the dog, and the other stuff. The building focus better on the building. Oh, yeah. So that's some method we developed. Okay. Just for your reference, maybe we can take a break for 10 minutes and come back at 4:45. Okay, let's take a break.这个128就是你在这定义的，
就是我
对
可以随便定义，
对，你可以随便定义。
不管这个 batch size 就是64的，
跟 batch size 没有关系吗？
就是没有关系。
这里可能有一些混淆的是，我们 batch size 也用了32，这里的 channel number 也用了32，这两个32不是一回事情。
这上32是什么？
这个32也是你自己定义的，就是说，你想按多精细的力度去让它产生分歧，因为原来可能3个 channel 太粗了，你希望它从不同的角度去看待你的这一个 image， 那你就从32个 perspective 去看待它，这个也是你定义的，然后你可以改这里，就是没有什么特别的。
然后就是关于 assignment， 然后我是用这个 Minix 的数据集训练，然后就不用自行收集就可以。
Minix 数据集那个不是一个gesture。
对，所以用另一种方法是，
就是这个的话，可能
就是把手的这个部分提出来，右边是把手的。是我提出来的东西，然后这个是
这你不是用自己的吗？为什么你用 Minix 你是用那个 gesture Minix 去训练是吧？那个 sign language 的那个嘛是吧？你说的是 sign Minix， 不是那个 Minix。
对不起。
sign Minix 它是一个 gesture。OK 啊，你这个就是说你相当于用的那个训练，如果你可以测一下它 accuracy 到底是多少。
对，我测了一下，然后用了好几个 cluster， 现在目前我看到的然后是0.8了。对，这个是正常的，是0.8。
正常啊，因为那个数据集跟我们这个差别挺大的。
OK。
然后多少个类啊？这么多？就是所有的都这么多，你可能需要有一个，你自己建一个 training data set， 你还是要收集一些自己的这一个作品，你才能够真正的量化的看到，就是说它工作的好不好。否则你只是这种一个一个 sample， 你可能有时候觉得还不错，有时候觉得不错，但是这种不错和不行，这种到底是到一个什么程度不知道。
就是还是要自己去收集一下。
对。
这个应该是想问民警，就是你不是问那个对手人
理论上来说是你们自己去收集 data set， 但是这个 Minix 就是一个 sample 一个 reference， 之前我们 tutorial 里边用过的，就是这里边就是要让你去你们自己 explore 这种 difference 到底是什么，用一个这个特殊的 environment data set 做 training， 然后在这个现实的这个 data set 里边。它的一个 performance 是什么样子的，然后最好是你对比一下我在现实里收集的 data sets， 然后又在现实里边用，他们俩的这个差别，这个就是让你们去 explore 这个过程。 你才可能真正的知道你要把一个application 或者是 machine learning theory based application 你需要做的一些事情。像他们现在做的就大部分的已经做了，比如说把那个手取出来啊，这一些其实就是现实，你在做现实的 application 里面需要用的一些东西。我看见已经有同学做的一个挺好的一个系统。
所以就整个方向就要换一下。
也不是吧，就是说你现在可能没那么多时间，你现在你学到什么，你就把它写进去，就是说，重要的是你学到东西。然后我们到时候会去汇总嘛，我们就会把那些关键的大家遇到的问题和大家发现的好的方案啊什么的，我们就讲，这样子你可以学到更多的东西。
然后遇到的一个问题是说，像刚才的那个 capture 出来了一个手的这样的一个，然后用这个去 predict， 但是有一个问题是我们这个手那摆成什么样子就 predict 都是label 的事情。这个是不是可能是因为图片它取得有点太复
是有很多原因的，因为它那个是个 control 的 environment， 非常理想的东西。也就是说，其实它的 pixel 之间的差异已经是非常大了，因为它基本没有什么背景，而你在现实中取的时候，你有不同的背景。
确实我已经是加过 contrast 的。
对，你现在 network 你是用的 neural network 的还是？
不是，之前写了一个 neural network，
现在就是个 SVM 的。
现在是什么
？Random forest，Random forest 也是一个比较传统的方法，就是对随机森林。随机森林的话，它通常对离散的数据要好一点。没关系啦，就是说 performance 最重要的就是说讲，就你关键是要知道好和不好，然后你遇到的一些问题，你想了一些方法去解决它。有一些自己的想法，因为这样子你才真正能学到东西的。否则的话，因为我们又不是这个职业培训学校，直接告诉你这个打螺丝钉该怎么打，不是这样的。就是其实所有的machine learning 也好啊，这些都是你怎么想是最重要的，然后你的 experience 也是非常重要的。
所以离 deadline 还有2个小时，应该可以来得及再搞。
对，你可以试一試，你可以試一試。
其實我而家都係做緊幾個事，做緊教咁呢個做 success 嘅其實係點樣？其實你做緊嘅咧係同啱啱講嘅一模一樣。我之前咧我係 mobile 嗰個 video 真係好大個 image 去做 application structure， 之後就執咗去我試佢做 model， 即係佢 base model 基礎嗰個 model 之後。即係我有173個嘅啫。其實佢原理上就係佢喺呢一個同步入邊，佢都會繼續玩一啲相類似嘅去做 training。
係啊，
係咪咁？
未係咁啊！我而家唔係打嚟咁嘅。
因為我有試過用其他 feature extraction，
你可以話你做
好盡，但係當我 put in 咗呢個 mobile， 因為佢嚟跟住同埋我哋呢個都上到 hand， 變相就已經我而家可以去到90至93。即係而家我呢個
係試唔同嘅 solution。
我有試過 SVM。跟住我又做咗啲大嘅，其實喺嗰邊我就係咪已經做緊啲嘢？因為我想知道，因為我嘗試翻對個 model 嘅，首先我就用咗同一個 feature， 就用佢嘅 training model 就喺個地方。之後我有試過用即係用 random forest 用同嘅 feature extraction， 去睇下有啲乜嘢 feature extension 係對呢一個 application。最尾我 find out 到係用 HOP 嚟即係 history gradients， 即係揾個 shape， 即係我揾啲 key point。
係啊，
因為原來 key point 係 drop 咗，咁係咪已經夠用？
因為你個手呢個 application， 你個手其實係冇幾多 key point。
我想起，即係無論你咁樣轉頭，定個 shape 咯，咁所以 HOP 就可以比較容易。
係啊。
但係我想問咧，即係我喺 report 有啲特別嗰啲嘢，但係 source code 我只可以交一個啊，咁你加唔加入到擺翻？
可以啊，你如果可以 upload 到，你可以俾
即係我可能攝晒已經，因為我呢度係試咗唔同嘅夾在上面。最尾我覺得最主要我都係用佢點樣，同埋我都即係我見即係 data mining 嗰方面都用，但係其實我就我想安排件事，我知咁樣會唔會乜嘢？
我覺得最重要係你死到，
因為你見我啲曲其實好短，呢樣就係因為我就係試得到用個 accuracy 去做一個標準，去睇點樣，因為
你寫低你做有個成個陣你點諗佢呢啲比較寫。
我有 data collection 係啊，跟住 feature extraction， 跟住揀 model， 去到 detection， 因為 detection 咧，我發覺我哋隻手喺度喐嘅時候，其實個 ROI 非常之好叻㗎。有時會 drop 咗個 IPS， 然之後我就用呢個，我就加
覺得幾好，
可以 polish move 落去，令到佢可以知道呢一秒 capture 就算佢喐咧都就係留住咗個 image， 咁就 smooth 咗。
呢啲都幾好，係 OK。因為
我都唔係好清楚嗰啲，我就用自己個 app。
呢個應該嘅話係 close， 所以係你自己死咗唔同嘅嘢。
因為我發覺有啲好勁嘅 model， 你用錯 feature extraction 佢都可以好多。
係啊，
因為個都唔啱。係啊，係因為好多人都話，其實我哋就 shift 嗰個 key point 去揾，即係好似你就唔一定係最好嘅，係啊，一定。我用 ORB 去揾啲 key point， 因為呢個係 live 嚟，我哋又要，我相信佢會好。其實我哋方法同學生係，即係其實咁樣，反而執好晒啲嘢就交
因為咧死咗你而家仲未試好嗰個 report 就
我都有寫，但係 report 即係如果我交個 source code，我 report 就唔使咁多 caption， 我直接成個 source code。
因為你死咗唔同嘢我哋 report 就最好咧就擺更多嘅 source code。係啊，你可以你可以有唔同嘅即係講嗰啲圖片啦，你哋擺翻嗰個 report。咁你好似你話咧呢個可以將佢哋嗰個你因為兩樣嘢都係唔同嘅。
我幾十 K 上。
係啊，
但係下邊我就冇就係都問你
你比如你話嘅 system 你可以你即係
capture performance，
即係話你有啲圖，你又有啲圖啊，有啲數據啊，support 你嘅
可能咁我應該係就係跟翻個 account 個情況，中間加埋係啊，我可以加埋收數，
可以都冇問題
因為個 requirement 咪只可以得一個 part。
其實我哋做唔起好似嗰個 source code 係最重要嘅嘢嘅，即係 source code 我哋可以睇到咧你做同埋你做到咩嘢。咁有你點做嗰個中間嗰個 source 係邊樣嚟嘅？呢啲嘢係啊，
都好
最開始你可以寫啲你
因為我都有寫字，我嘅白色嘅，跟住發現咗 problem，最尾就咧嗰個 approach
你可以俾住你你個 source code 個respondent one folder is formatted one other folder is formatted two different files。
可能方便係寫翻邊個收
係啊，
佢 refer
係啊，咁樣會好啲咯。
咁就唔使
可能直接擺會好啲，圖片會好啲咯。係啊，圖片會好啲，佢俾人哋知手機俾人知呢行straightforward 俾你睇。
我想問個 submission format 嘅，因為咧嗰個 requirement 寫到好 specific 嘅，就一定要得兩樣嘢。但係咧，咁我就用咗呢一個 dataset，咁就都頗大。咁我如果先還佢，我驚賺到個 TA 喎。
哦，
咁我諗緊，
你而家帶過嗰部分，你 dataset 好大嘅。
dataset 因為佢呢個係 new image，即係佢幾多嘅 A， 即係每一個 list 有3000個，跟住就 A to Z 再加 space nothing。
你可以咁樣做咯，你揀啲 sample 出嚟，你構成。你唔使成個 dataset 最貴，你可以寫低嗰個 report 就係話我係用咗呢個 dataset 俾你，但係因為佢太大，所以我唔可以啱，所以我就 up 咗個呢啲 samples 俾你哋。同時咧，我用個 dataset 嘅 link 喺度俾個手。
即係寫個 repeat 嘅時候，
係啊，寫同
好似咁樣。
code 你哋寫report 嗰度都可以寫。
哦，即係可以呢當乜單咁樣。
係啊，兩邊都寫，話俾佢知啦。總之呢個 data 就太大，我可以 send 俾你。
個問題而家。
Okay, let's just continue on the topic. So, last slide is actually we developed some camp. You can check it out. And also another thing is we could use the probe to check if the network is focusing on the right part. However, you may raise another question. In case it's not focused on the right part, what we can do about it? Can we force the model to focus on something we want? So this might be a question will come to your mind naturally after we say there are some probes can help you with that part. So there is indeed something called attention mechanism. Attention is something like we're helping the network to pay attention to a certain part of that image. So this is actually quite straightforward. And this diagram I actually is the one where the attention mechanism as a term is first used in the paper. So I use that image. But this part, they're using the attention is kind of complicated. So I actually masked it out. Let me introduce the idea in a very straightforward way. Then we can check it out with that exact structure is used. So the idea is, like when we're introducing that can, we know that spatial dimension of the original image will be preserved in the feature maps, right? So how about if we have some kind of mask, like here, if here is a person here, you see in this image, there's a person here. If we really want that network focus on that image, so we could use a mask. In that mask, the weights are given. if let's see, it's a correspondence position of that, because I mentioned the spatial dimension have been reserved. So if we can put higher weights on the part we want network to focus on, we can apply this mask to the correspondence feature map. Meaning like when, let's see, let me just grab one of that. Let's see, this is a feature map. And here is a mask. We can multiply this feature map on the spatial dimension with the weight mask we have. So let's see those parts with higher weights. Meaning that after the multiplication, and those neurons will be better activated at the other part, right? Because we are actually improve, because those are with higher weights. And after multiplication, those parts with the higher weights will be more better activated and the other part, because the other part with the smaller weights. So in that case, we can force the network to focus on some part we want. So this is a very straightforward explanation of the attention. So once we can have that weights created, then network will focus on the right part. However, this is just a way of explaining it. In practically, you can actually learn those attention matrix, and network learn the matrix by itself. So check out, this is actually a network. They insert such kind of mask at different positions, meaning like it's taking out this feature map after the 7th convolution, after 10th convolution, and the 13th convolution there. So you got different feature map there, and you can summarize them together and send them to the fully connected layer to help out the final decision. So this is the way actually doing it. And here's the results. You can see like those are different feature map at different position. And this is what is supposed to focus down. And this is what exactly focus down. You can see it worked well by forcing the network to focus on the right part. This is called attention mechanism. It's a way by applying attention to force the network to focus on the right part of that image. However, it turns out what we have introduced in previous slides, we are forcing, we're using attention on the spatial dimension, right? But it's actually, you can use a similar idea on the channel dimension, because different channel, some of the channels may tell better information than others. So we should have a network focused on that's good channels than those poor other channels there. So that's the idea. You can use the channel attention. This is a very successful attention mechanism called CBAM, which combine the channel attention and the spatial attention together. Making the network can focus on the right channel and the right position at the same time. So it's quite successful, and this is network a bit. So let me explain a little bit here. By channel attention, you can use the maximum pooling on that channel, and you can, because you don't know actually which one will be better and which one will not so good. So you can use a fully connected layer, or sometimes we call it MLP, meaning multiple fully connected layer. You can think of it that way. Use this network to figure out a right focus on the channels and to summarize these two perspectives together as a final channel attention. And this channel attention is a weight. It's a weight at a vector. This vector will be multiplied on the original feature map here, meaning that the corresponding position will be multiplied to the corresponding channels here. So one channel has one weight. So we're weighting the channels using the channel attention. And the spatial dimension stuff is the same as we have introduced previously. You could have some weights along the spatial dimensions, and so it can focus on the right objects at image. So this is a way to combine the channel attention and spatial attention together. However, that's the attention mechanism. I think that's quite straightforward, right? So is it okay for the attention mechanism? Right, that's quite straightforward. Let's go the self-attention part, because this is the last concept we're going to introduce today. And it's actually the idea of the transformer. You probably already heard about it. Transformer is quite popular today. And, you know, just in this morning, the GPT-4 has been released, and it's, I'm pretty sure it's based on transformer. Nowadays, almost all the large models are based on transformers. So it's quite important. But the idea itself is not that difficult to understand. So that's the reason I put it the last part. It's quite important, and I want you to get more insights of what's happening to you. Transformer and self-attention is a mechanism. It's one of the main ideas of the transformer. So it's quite important. So it's a different types of attention mechanism at the same time. So let me introduce what the self-attention is. Because the idea is actually from the NLP domain, meaning that they're processing the sentences, the text information there. So it will be better if we use sentence rather than an image. And later I will explain how you can extend this idea to image. So let's start with the sentence. Let's see. This is an apple. Run make something which tests good. So, let me just make one sentence, not the perfect one, but just trying to give you some example. So you see, here's a sentence, and there are different words here, and you know that some of the words actually are related each other. I mean, it's better related to each other. Like this apple, good. So this is basically what this sentence is trying to say, right? So they are related better than the relation among them is more tight than others. So the self-attention trying to figure out some kind of relationship like that. So, but how we can do it? So the first thing we will do is a process called embedding. Not easy to write, use this. Okay, so the first thing we're doing is embedding. Embedding is a process to transform a word is a text into vectors, meaning that for every word here you have a vector. So there's a vector because the computer knows numbers only, as I mentioned another time. So you have to use a vector rather than original text information to do the process. And at the same time, when you're using vector, the dimensions of the vector are the same. It's easy to do the calculation like those calculation you can apply on the vectors, because right now they're all vectors. But how we can get the embedding? There are different ways. Let's see, if you're interested in that, here is a word to vec. That's a very popular method by converting a word into a vector. But that's it's kind of beyond the topic today. Just remember, there are some way you can convert a word into a vector. And also you can actually convert the position. For example, this is position 0, position 1, 2, 3, 4, 5, 6. You can add that position information into that vector as well. So this is just vectors. After the embedding, all the words becomes vectors. Then you can do something on those vectors to learn this kind of relation. But how we can do it? So the process will be started like you're evaluating the correlation among different words. Let's see, right now we're studying the word this. It's the first word. So we can calculate, let's say, we can calculate the cosine similarity with different words. If that embedding works well, and so this vector should capture the semantics of those words very well. So in that case, you can calculate the semantic similarity to different words. Then you have a weight similarity as weight 1, weight 2, weight 3, weight 4, weight 5, weight 6, and so on and so forth. So then you can do something like using those weights by applying to, by summarize this vector. Let's see, this is weight 0, this is vector 1, vector 2, vector 3, vector 4, vector 5, 6. And then you can summarize this part and you can put them together with the 0, 1. So the 0, 1 will be updated like you can do something like this. And this is supposed to be average of it. So I will skip that. So this is a very straightforward way. By doing this, what will happen is, because those are tightly related, so they are supposed with higher similarity, right? Meaning that those weights are larger than others. And when you're fusing those vectors into the first words, and those information will be added back to the first words. Meaning like after this process, the first vector will carry some semantics of those tightly related words in that sentence, right? So it is okay, right? So if everything works well, and you can repeat that process for all the vectors in that sentence, then you have V0 prime, V1 prime, V2 prime. In the same way, V3, wait for five, 6 prime, something like that. So you can apply that kind of procedure for all the words here. So after the process and those tightly related words, after that process, will be, their information attend to with higher similarity to each other. Because by doing this, you're forced that process to having such kind of result. So this is like you're using the inter-word correlation to create something we call representations. You can consider it as a feature vector for different words. And after the process, those words will carry in the context information of that sentence. And so this is basically a very simple explanation of self-attention. The self-attention right now is the attention, because these weights are considered attention as well. So it's an attention inside that sentence, inside that context. So making those words help out each other to create collaboratively for a final representation of feature vector. So this is basically the idea used for transformer, but not exactly, because I'm just trying to simplify the process. So if this is okay, we can go in better details. So it is okay, actually, the self-attention, right? It's okay, right? Very simple. So what used exactly in the transformer is something different from here. Maybe we should came here and let's generate one empty retention transformer. Oh, let's put one more slide for. Let's take the same sentence and what exactly used in transformer is something like this. This is an apple, which tastes good. In a transformer, still you have to do the embedding stuff. It's the same like what I've introduced. Okay, you got several feature vectors, but at the same time, the transformer will create something like, let's see, this is, let me give a number to each of the words. Okay, so you're going to have something we call, for each word you have a query vector related. So this is like the Q0, Q1, Q2, Q3, Q4, Q5, Q6. This Q stands for query. And let me use another color. So at the same time, you have query, then you have query key. It's another vector k0, k1 here. K2. I'll not write the numbers, and you know what it is. And to save time, and let me use different color. Let's see, we have this one. Query key value. The third vector corresponding to each words. You can see here we can get each word 3 vectors related, and they are corresponding to query words, key word, and value word. Why we have those? I will skip the part how to create when I will introduce later. Why should we have 3 vectors related to one word? It's actually from the retrieval. So think of like when you're searching on Google, you have some keywords there, right? So these keywords are considered as queries, right? And recall what we have introduced in the image retrieval. We have an indexing process. The indexing process actually will, it's a way like when you're making dictionary. In a dictionary, you have in the table of contents, you list some of the words there and show the corresponding page number there, right? So when you're making a dictionary, they are indexed by those words. Okay, so that word is keyword. When we're searching something, it's like we're compare our query to the keywords there. Right? This is searching, and search engines actually work in that way. You index some of the pages using keywords. Like I got the keywords of Apple, and I will put all the web page containing the word Apple after that as a volume, right? So you could see the retrieval process is from query compared to the keywords. And when you located the corresponding keywords, then you can find the actual value related to that keywords, right? So this is the idea of query, keyword, and the value. So meaning like one words in different contexts, they have different roles, right? Sometimes it can serve as a query to search other words there. Sometimes it will be used the keywords to indexing some stuff, and sometimes it will be used as a value. So there are 3 major roles of a word can be used in a sentence or in a document, right? So that's the reason we have 3 words there for each of them, and this can be created very easy by you can consider this is a process like extending the number of channels, right? Because you just have to let them connect it, and network after back propagation will figure out what exactly it is, that vector it is. So there's a better way to generate it. So what used in the transformer is they are comparing, maybe use different color. What they are doing is very similar to the process I have introduced slightly, but it's just with a very slight modification. To generate Q1 is compared to the keywords here, rather than compared to the query directly, because the searching process asking defining the way like we're comparing query to keywords. So it would be something like that. So meaning like we're calculating the similarity between the query and key, right? And after we have that, we apply that similarity on the corresponding value. So those are the value. So after that, you can summarize, you can change that a little bit, like you're using the similarity between certain words. Let's see, we're summarizing for the first words. Let's see, we're trying to get something like for the first words in the next iteration. Let's see, we're looking for a representation for the first words. Then it's a similarity between the query 0, it's here, and the corresponding key here. So this is a similarity. Then after calculating the similarity, we can actually multiply the corresponding value. So we are using those similarity as an attention to apply on the corresponding value here. So those results, like what I showed previously, will be to put together on the words currently you're investigating. So you can repeat that process here. So that representation will be changed by using those weights or attention here. So this is exactly what the transformer is doing. It's not that hard to understand, right? So putting those together, you will see this is what exactly transformer is using. So they are using they are defining it as vector operations there. This is like calculating the similarity. Because this is inner product when the vector anomalies are exactly the similarity, right? And also they use a scaling factor to avoid a situation like the inner product is too large or too small. Anyway, they are trying to control it into a certain range. Then use the softmax. It's the same, like we mentioned previously. Softmax mapping the value you have into the range of 0 to 1. It can be better used as a probability or similarity or attention score. Then you use that weights apply on the vectors there. Then you have that kind of attention created for these certain words. So this is called self-attention. Then you could see the process will be something like corresponding to here. You have a query, have a key, and you multiply them together. It's this part. And then you scale it. It's this part, this part. And yeah, you do the other softmax stuff. And this is the process to combining them. Okay, this is self-attention. And so is this clear? Okay, right? Okay. So, and you can see this can be used on image as well. You will see the self-attention will help you the right part to help the network focus on the right part as well. But what's the difference between this transformer attention, self-attention, to the attention mechanism we have introduced? What's the difference between them? Maybe I should introduce how it's used in the image first. So, you know, we got some words one by one, but in the image, we just got pixel. If you're using one pixel as a word, you got too many words there, right? The computation load is pretty heavy. So it turns out the most popular way is we can divide them into patches. We can use each of the patch as one word. Then you could check it out in the transformer structure I've introduced previously. Those are word 1, word 2, word 3, word 4, or something like that. Those are just words. So the structure I presented previously can be applied directly on the image after this setting. So you can learn the inter-patch attention, like we're doing the inter-word attention of weights, right? So this is how it's used for image, and it will give you some kind of result like that. But the question back is, what's the difference between this transformer attention and the attention I have introduced previously? What's the difference between them? Anyone have some idea in mind?
For the previous methods, you need like supervised input where you need someone to tell you where the area of attention is. Whereas here it figures it out on its own compared to the previous queries.
Okay, that's great. That's actually a great perspective. Yeah, that could be one. I will explain this one later more. There is one essential one. It's actually a difference between the convolutional network and the transformer. Do you realize there is something different between them? The transformer structure and the convolutional structure. To remind a little bit, the convolutional structure we introduced so far is like you're applying a filter on that image, and it calculates, it's filtering or summarizing some of the information under a certain window. It's a filter at the same time, right? So it's the window is sliding over that image along the spatial dimension all the time, meaning like it's summarizing the information of a local area, right? So in that case, convolutional network is actually are working well in those local attention or local information. Okay? However, what we have in the transformer is like, it doesn't matter where the patches is. It could be one, when you're doing that, this patch could have a very much higher attention with this one, right? Because the words, there are words. When you're calculating it, you're doing something like that. This is called long-range attention. Well, with the convolutional networks, it's not easy to figure out the correlation between this part of the image to this part of that image, because it might be possible, but it's not that straightforward, because you have to use a convolution gradually, layer by layer. Finally, those information of this part might be transferred to here with a lot of convolution there, right? But transform quite straightforward. You begin that calculation at stage 1, because you calculate the correlation between the patches. You have the long range attention there. So this is an essential difference between them. When you're doing the attention and you do the same, you have long range attention there rather than the local attention. Okay, this is one essential difference between them. The other one raised by Marlon, I think it's quite interesting, the question he raised. It turns out something like, even we haven't introduced that part, but you actually got the point. So a transformer can be used. Transformer can be used. Let's read with the look at this part. This is actually the part we mentioned previously for self-attention part. And after that, for each of the patch, you have one representation at the end, corresponding them to one by one. So these parts currently highlighted is the part like you can add some fully connected layer to the representations to make the to do the classification task, right? So this will making it back to the supervised learning, because in the classification you gave a label and you evaluate the loss. Then the loss can during the back propagation, the loss will be back propagated through that process. What happened? What happened? Saying a connection loss. But fortunately, you're still seeing it. You know what happened, but we have to do it fast. So the back propagation will be something like you have a loss here, and the loss, the gradients will be back propagated in the same way like we have introduced previously, because this network up. Okay, so we're having some problem on the connection. So let me just, I don't know what happened. So we can just use the whiteboard. And so we're going to have, this is transformer part. We got different patches there as the inputs. After transformer, we have representation at the end. And you can use this representation to aid the fully connected layer for reasoning. Then you will have a label output as a prediction. Okay, so this is basically the same with what we have introduced previously. The only difference is this part. Previously is a convolutional network, right? Right now it's a transformer. But the back propagation will be very similar back from here. And you can use the exactly the same thing to do the updating. So Bernard raised one very interesting stuff is he's saying like when you're doing with transformer, you don't have to go through the supervised learning. How do you reach that point? Well, what make you comes out that conclusion?
Because you have the queries that are associated already with the words. Okay. So you just compare it already, and then they get updated automatically.
Okay, that makes sense. If you're talking about words, the words have some semantics for each of them related, so you can calculate that part. But what happened in transformer is not that way, actually. But that's kind of understanding can be borrowed here. So what exactly happened is we don't actually define the similarity by ourselves. Like you could figure out the semantic similarity among words, but for image patches, it's impossible doing so because image patches doesn't have defined semantics related, right? So it turns out you can so the self-learning, or unsupervised learning stuff is one very important feature for transformer. What they are doing is like, let's see. Let's take out the sentence again. This is an apple, which we can ignore in other words. So I guess it's enough. So you're going to have representation here, right? So what Marlowe is mentioning is from very straightforward common sense. But what exactly happened here is in the NLP domain, they figure out a very smart way for creating the representation and for conducting the training. So which is we can ignore this part. When you're doing the training for this part, you can temporarily ignore this part. You can take out this part to count out some kind of task we call MLM. It stands for Masked Language Model. Masked Language Model meaning like you can mask out some part corresponding to those words, like here we're masking out this one, masking out this one. But at the same time, we can use the rest of those words to predict what those words is. For example, it's like right now we know this is a this is an and, but we don't know this is a this, right? We're trying to use the rest of words to predict the this because we have that sentence there. We just mask it out intentionally, so we can compare this representation to the representation of the is, right? So if in case it's making a correct prediction and the loss is low, in case it's making a wrong prediction, loss is large, then we can use that loss to back propagate to update the gradients and parameter of the whole network. In that case, we don't have to give labels because the label created automatically during the masking process. And we can repeat that process multiple times by masking different words there. In that case, we don't need any of the labels, and it's updating the weights automatically. So this is a self-supervised learning process. And that's the reason making this large model possible. You know, those large models are really large. They got thousands of billion parameters right now, right? So this is a technical trick to make it possible for training in that sense. And taking that image patches, you can do the same. Because for an image, after you divided them into patches, so you're going to have different patches here. You can mask out some of them up here using the rest of parts to reconstruct those patches masked out here, like here, right? So you can start the training automatically without giving specific task to it. So this process is called pre-training. So this is a pre-training process trying to create a network which can create tokens for you automatically. And it's not associated with specific task. After training, you can use this pre-trained work by associating them into specific tasks like prediction, object detection, and other tasks there as well. Okay. And is this clear enough? Okay, very good. Okay, I guess that's it for today. The network is broken, so I hope this explains the stuff. Okay. Okay, thank you very much, and I hope you enjoyed it. And this is our lecture 9, and see you next week.